Alright, so number one, this one says that we've got a charged ion that starts from rest. So it doesn't tell you what the charge of the ion is. So I'm just going to go ahead and say that the charge of the ion is Q. Okay, that's the symbol for charge. And it says that it starts from rest, so what is the initial velocity of that ion? Zero. Excellent. It also doesn't tell me what the mass of the ion is. It's important to note that this is not an electron, this is not a proton, this is just some ion. So it doesn't tell you what the mass of the ion is. So let's just say that the mass of the ion is m. And it says that it's going to accelerate through a potential difference of 1 kilovolt. So it's going to start here, and it's going to accelerate through a potential difference, so between 2 points A and B, and there's a voltage difference, there's a potential difference delta V between those 2 points. Okay. And the potential difference between those 2 points, they tell you, is 1 kilovolt. So remember the prefix kilo means what? 1,000, right? So that means that the voltage difference between those 2 points is 1,000 volts. Okay, so there's 1,000 volts of potential difference. Alright, so now, here's the thing. So now, does everybody agree that it is accelerated through that potential difference? So now it has a final velocity, which I'm going to call V final. Does everybody agree? So now it says that it enters a region where there is a magnetic field that is oriented perpendicular to the motion of the ion. Now, does everybody agree that perpendicular to the motion of the ion could mean 4 things? Does everybody agree that the motion of the ion is in this direction? Would you agree with that statement? So there are 4 possibilities for perpendicular to that. Does everybody agree that one of them is up? The magnetic field would be up. Does everybody agree? The other possibility is that the magnetic field is down. The other possibility is that the magnetic field is into the board. That's in the negative Z direction. The other possibility is that the magnetic field is out of the board. Okay? All 4 of those are possible. Now, if the magnetic field is up, the actual orbit will be in a plane that comes out of the board, like this. Same thing if the magnetic field is down, the orbit's going to be in a plane that is perpendicular to the board. So you don't want to actually make your field this way or this way. You want to do in or out. Those are the only 2 that you want to do to be able to visualize the orbit. Okay. So if they don't tell you if it's in or out, you can actually choose any of the 2, and your answer shouldn't depend on that choice, right? So in this case, I'm going to say that the external magnetic field that will be affecting this charge will be into the board. Okay. So this is going to be B external. So is this the magnetic field generated by the ion, or is this some external field that will affect the ion?
External.
It's an external field. Okay. All right. So now here's the thing. The question is, if it enters this magnetic field, and what is it going to do when it enters that magnetic field? Since it's charged, what's going to happen to it? Does everybody agree that it's going to get deflected? Does everybody agree? So it's going to get deflected, and it's going to form some type of orbit, okay, inside of that magnetic field. And there's going to be a radius to that orbit. The radius of that orbit is 5 millimeters, as given in the problem. Okay. And the external magnetic field is 0.040 Tesla in the negative k hat direction. Okay. Why negative k hat? Because into the board. Excellent. All right. So now the question is, what is the mass to charge ratio of that ion? In other words, what is the mass divided by the charge of this ion? Alright, so I'm going to do this as a 2-stage problem. How so? Can I figure out what the final speed of that ion is? At least in terms of the mass. Can I do it? And the charge. Let's see. So I'm going to do this part of the problem first. Okay. This is a closed system. So since this is a closed system, I can use conservation of energy. Potential initial plus kinetic initial equals potential final plus kinetic final. Does everybody see that?
Yes.
So now, take a look. My potential energy here is an electrical potential energy. Not a gravitational potential energy, but electrical potential energy. How do I write the electrical potential energy U in joules in terms of the voltage? How do I write it? QV, charge times voltage. So this guy is going to be the charge of the ion multiplied by the voltage at point A. Okay, multiplied by the voltage at the location where the charge is initially, which is point A. Okay, plus, what should the kinetic energy be of that ion when it is at point A? Remember, it says that it starts from rest, so how much kinetic energy does it have? 0. Excellent. So this term is actually 0. equals potential energy final. So that's the potential energy of the ion when it gets to point B. How do I write the potential energy in terms of voltage? That's going to be charge times voltage. But this time the ion is now at point B, so I need the voltage at point B. So the potential energy that the charge possesses when it is at point B will be the charge of the ion multiplied by the voltage at the location B. Plus, does everybody agree that now it's going to have some kinetic energy? Does everybody agree? So its kinetic energy will be 1/2 mass times the speed at point B squared. It's important to note that there are two V's here. One V is the voltage, that's the capital V. The lowercase v is the speed. Does everybody agree? Everybody see that? Now, here's a question for you. Conceptual question. What has happened to the electrical potential energy? Has it decreased or has it increased, and why?
Decreased as the speed goes from 0 to a positive value.
Potential energy, then. What has happened to the potential energy? So remember, U plus K has to be a constant, right? This is a closed system, so the total mechanical energy has to be fixed. Does everybody agree? So if K goes up, would you agree with me that K is going up? Because the charge is accelerating, it's speeding up. Would you agree? So if K goes up, what has to happen to U? It has to go down to keep the sum what? Constant. Does everybody agree with that statement? Now, but U, for electrical potential energy, is the product of charge times voltage. Would everybody agree with that statement? The charge doesn't change. Does the charge change for the ion? Does everybody agree that it does not? So does everybody agree that just because the potential energy decreases, does everybody agree that the voltage at point B has to be lower than the voltage at point A? Would everybody agree with that statement? Why? Because what is happening to the voltage? It is decreasing. So in other words, this charge is going from a region of higher voltage to a region of lower voltage. Does everybody see that? Okay. So we're gaining kinetic, so we're losing electrical potential energy. So that means that we are going down in voltage. That's of course assuming that the charge is positive. Okay? If the charge is negative, it's the opposite. Alright, so now, take a look. What I'm going to do is I'm going to go ahead and solve this equation for that final speed. So does everybody agree that I could actually subtract QVB from both sides? Does everybody agree with that statement? I just subtracted it. Did the charge change, or is it the same? Same. So I could factor it out. So it's Q times voltage at A minus voltage at B is equal to 1/2 mass times the speed at point B squared. So what I'm going to do, I'm going to multiply both sides by 2. So I have 2 times the charge times the voltage at A minus the voltage at B equals mass times speed at point B squared. Now, assuming that this is a charge that is positively charged, we won't lose any generality because if we assume that it's negatively charged, we're going to get the same result. So it doesn't matter. So assuming that it is positively charged, does everybody agree that this charge has to go from high voltage to low voltage if it is in fact gaining kinetic, right? What did we say here? It gained kinetic. So what had to happen to the potential energy? Had to decrease, and therefore since Q is positive, what happened to the voltage as the charge moved from point A to point B? It decreased. So it's going from a region of higher voltage to a region of lower voltage. Does everybody see that? So that means this difference here is a high number, so it's a positive number, minus a low number, which is a negative number. Does everybody see that? So a positive number minus a negative number ends up giving you a positive number or a negative number? Positive number. Does everybody agree? So this voltage difference is positive 1,000 volts. It does not need to be positive 1,000 volts. It could be negative 1,000 volts. Does everybody see why this is positive 1,000 volts? Does everybody see that? So this is 2 times Q times 1,000 volts, that was given, is equal to MVB squared. So this now gives me 2,000 Q is equal to MVB squared. Does everybody agree with this statement? 2,000 Q, 2,000 times the charge of the ion, is equal to the mass of the ion times the speed that it has acquired after accelerating through 1,000 volts of potential difference, squared. Okay. Now what were we after? What were we looking for? Mass to charge ratio. Does everybody agree that what we are looking for is not the mass and it is not the charge, it is the mass over the charge? Does everybody see that? Is the mass over the charge present in this equation?
Oh, well,
Well, the mass is, and so is the charge. Does everybody agree? But there's a variable in the way. Does everybody agree that before I calculate the mass to charge ratio, I first have to figure out what the speed at point B is? Does everybody agree? So what part of the problem have I not explored yet?
The external field.
When I'm inside of the external field. Excellent. So let's now draw that guy. So here's the ion, and it comes in, and it's going to get deflected by the field, right? So there's an external magnetic field, not the magnetic field actually generated by the moving charge, but an external field that will affect the moving charge. So here it is, and just out of curiosity, if I give you this picture, immediately you should be able to tell me if that's a positive charge or a negative charge, just by showing you that picture. So is it positive or negative, and how can you determine that? Right hand rule 1 or 2? 2. 2 is for force, 1 is for field. Okay, so here's the charge moving. Okay, suppose that this is some velocity, and let's say it's a positive charge. Okay, right hand rule 2, you have to take your right hand to determine the direction of a magnetic force acting on a charge by an external field, right? You take your right hand, you put it in the direction, your fingers in the direction of V with your palm facing the field. So what does the X mean again? It means the field is pointing into the board. That's what it means. So I'm going to take my right hand and I'm going to put my palm facing the board because the field is pointing into the board, right? My palm has to face the field. So does everybody agree my fingers are parallel to V and my palm is facing the board, facing the field, because the field is into the board. Now look at this. I'm going to curl my fingers towards the field. Remember, the field is into the board. Curl my fingers into the board. Which way is my thumb pointing? Up. Okay. Now, remember what we said. If that was a negative charge, does everybody agree that it would be the opposite of that? So if it's a positive charge, it's going to feel a force that is this way. Would everybody agree with that statement? So that is a centripetal force. Does everybody agree that it's pointing towards the center of curvature? So at a later time, this charge is now going to be moving in this direction, and if you apply the right-hand rule again, you'll note that the force is actually in this direction. The center is somewhere around here. The force is in this direction. Does everybody see that? So this object, or this charge, will actually deflect upwards, and it'll go into a counterclockwise orbit. Does everybody see that? How we got that? All right, so now, here's the thing. So is it positively charged or negatively charged according to my picture? Positively charged. Okay. Now, here's the thing. Does everybody agree that it doesn't matter where I do this calculation, I'm going to get the same answer? Does everybody agree? So let me do it right here. Here's the ion, and I'm going to do the calculation right here. I'm going to sum forces in which direction? X or Y? In Y. I'm going to sum forces in Y, and I'm going to set that equal to mass times acceleration in Y. At this moment in time, just like any other orbit problem. Same thing like with the satellite orbit, right? Same exact thing. So what is the only force acting on that charge right now at this moment?
Magnetic force.
The magnetic force. Gravity is also acting, but what did we say at the beginning of the semester? It creates a correction that is 36 decimal places past the zero, past the, So it's going to be such a minuscule correction to the final answer that we just neglected. So the only force acting here is the magnetic force. So I'm going to call that FB, and it should be negative. Why is it negative? Because it's pointing down. So we're going to sum that, so it's going to be negative FB is equal to mass times acceleration, and the acceleration is centripetal acceleration. Is it changing speed or is it changing direction, and why? It's just changing direction. Is it speeding up, slowing down? Why? If I ask you to explain, why is this object not speeding up or slowing down? Say that one more time. That's true, but there has to be an explanation. Say that one more time.
Force is changing the direction.
That's true, but you're just restating it. You're not explaining why that force is not changing the speed. There is a reason why it's not changing the speed.
Because the magnitude of it doesn't change. The magnitude of the force is
Perpendicular. Very good. It's perpendicular to the velocity. So if it's perpendicular to the velocity, therefore at all moments in time, what can you tell me? The force is perpendicular to the motion. A force that is perpendicular to the motion does no work. And if it does no work, it cannot change its kinetic energy by the work energy theorem. So that charge will not speed up or slow down within that magnetic field. It will just, be in uniform circular motion counterclockwise. The speed will not change. Only the direction will change continuously. So it is, in fact, the centripetal acceleration. That's the rate at which the direction is changing. So the negative signs will cancel. So we're going to be left with FB is equal to mass times. And what do I need for the centripetal acceleration? That's going to be what? V squared over R. Excellent. Now, FB, the magnetic force, that's the magnitude of the magnetic force. If you remember the magnetic force equation, the Lorentz force, QV cross product with B. Okay. So we're going to go ahead and write the magnitude of that. That's going to be the magnitude of Q, magnitude of V, magnitude of the magnetic field, times the sine of the angle between the two. Remember, the magnitude of a cross product, if you remember, this is going to be the magnitude of Q, magnitude of the first vector, magnitude of the second times the sine of the angle between them. Okay, so that's the magnitude of the magnetic force. And here, what does theta represent? It represents the angle between these two vectors. It represents the angle between the velocity vector and the magnetic field. But wait a second, though. The magnetic field is pointing which direction? Into the board, and the velocity is always pointing in that plane. Does everybody agree that the velocity is always pointing like this? So at all moments in time, what can you tell me about the angle between those two? It's always what? It's always perpendicular. Does everybody see that? So that velocity vector is always in the plane of the board. Does everybody agree with that statement? And the magnetic field is perpendicular to the board. So would everybody agree that velocity is always perpendicular to the magnetic field, in this case? Does everybody see that? So therefore, what angle would you use here? 90. Remember that angle is the angle between the velocity and the magnetic field. So that's going to be mv squared divided by r. What about sine of 90? What's that? 1. Excellent. So qvb is equal to mv squared over r. So this is like qvb equals mv squared over r. Okay, so now, one of those v's cancels. Does everybody agree that I have a v here and I have a v squared here? What's going to happen? One of these v's is going to cancel with this guy, one of these guys. So now I'm left with the following. So now I'm left with qb is equal to mv over r. Can I now figure out, do I have enough stuff? Q, do we know what the Q is? No, that's the charge of the ion. We don't know what that is. Do we know what the magnetic field is? Yes, that one is given. What's the magnetic field strength, the magnitude of the magnetic field? 0.040 Tesla. Okay. So we do know the magnetic field. We don't know the mass. Does everybody agree we don't know the mass? What about the speed? Do we know the speed? No, we do not. That's the speed at point B, by the way. Why would that be the same as the speed of the ion when it comes in? Because there is an acceleration, though. Remember, centripetal acceleration. But why can't I claim that this speed in this equation is the exact same speed that that charge had after it accelerated through that potential difference? I just mentioned it not too long ago. Is that force doing any work? No. So therefore, what is the change in kinetic energy? 0. I'm going to ask you to mention them. So tomorrow I'm going to have you explain in words why you're doing every step. Okay? So it's very important. So if I ask you, why is it that you can set this speed to the same speed everywhere within that orbit, that's what you have to mention to me. Okay. All right, so here we go. So this speed is the exact same speed that appears in this equation, the exact same speed. So we can now say Q times 0.040 is equal to m times the speed at point B over the radius. Now, do we know the radius of that trajectory?
Yes.
What's the radius of the trajectory as given in the problem? 5 millimeters. So I'm going to go ahead and convert that. That's 5 times 10 to the minus 3. Okay, so what I'm going to do is I'm going to go ahead and multiply by 5 times 10 to the minus 3. So I have Q times 0.040 times 5 times 10 to the minus 3 is equal to MVB. Okay, so let's go ahead and just plug that in and see what we get. So that's 5 times 10 to the minus 3 multiplied by 0.040. So I get Q times 2 times 10 to the minus 4 is equal to MVB. Okay. And I'm going to divide by M. So if I divide by M, does everybody agree that I have an M here? Does everybody agree? So now I have a VB here. And what I'm going to do is I'm actually going to square both sides. What would be the logic behind that? What would be the logic behind squaring both sides? So I could plug it in here. Look here. You have a VB squared. Does everybody agree that we have a VB squared in that equation? So if I were to square both sides of that equation, I would have VB squared is equal to something. And then I can plug it in there. So I'm going to square both sides. So V squared is Q squared over M squared times that squared. Okay. So let me rewrite that guy now. So the left side of that equation is Q squared over M squared multiplied by 4 times 10 to the minus 8 is equal to VB squared. Okay, does everybody see how I got that one from here? Does everybody see that? So now, what would I do next? I'm going to substitute this guy right in here. Okay, so I'm going to have 2000 Q is equal to M times VB squared, which is Q squared divided by M squared, times 4 times 10 to the minus 8. Okay, does everybody agree with this statement here? Does everybody see that? Okay, now look at this. Does everybody agree that this M is going to cancel out one of these guys? Does everybody see that? And this Q is going to cancel out one of these guys. So I'm going to be left with 2000 is equal to Q over M times 4 times 10 to the minus 8. Does everybody agree with that statement? Okay. I'm going to divide. So I have 2000 divided by 4 times 10 to the minus 8 is equal to Q over M. So let's see what we get here. So 2000 divided by 4 times 10 to the minus 8. So I'm left with 5 times 10 to the 10th. But wait a second. Was I looking for Q over M or was I looking for M over Q? M over Q. So to get M over Q, and by the way, what would the units be for this? What are the units for the numerator? Charge? Coulombs. And what are the units for mass? Kilograms. Right? So coulombs per kilogram, but I'm not looking for charge over mass. I'm looking for the mass to charge ratio of this ion. So that means all I have to do is invert both sides. So Q over M to the minus 1, which is M over Q, that's going to be equal to 5 times 10 to the 10th coulombs per kilogram to the minus 1 power. So that means the mass to charge ratio is going to be 5 times 10 to the 10th and then to the minus 1 power. So I have 2 times 10 to the minus 11. And what are the units? It's mass, which is in kilograms, and coulombs. So kilograms per coulomb. Okay. So question, if I had the charge of that ion, would I be able to figure out the mass immediately?
Yes.
Yeah, because I would just substitute that charge here, multiply both sides by the charge, and immediately I know the mass. Does everybody see that? If I knew the mass of the ion, would I be able to figure out the charge? Immediately, right? So just plug in the mass here and then I can solve. Okay, so any questions on number 1? Is everybody comfortable with number 1? Okay, so let's